Okay, so the final series we're going to take a look at is another three-part question. This one deals with a dragster and a driver. Together they have a mass of 884.1 kilograms, at least with my numbers. And so we've got the following. I was never particularly good at art, but we have our dragster and we have a driver inside of it. Together they have a combined mass. I'm going to put that as a capital M, just so I know that that's kind of the big mass involved here, and that is 884.1 kilograms. The dragster, starting from rest, attains a speed of 26.6 meters per second in 0.65 seconds. All right, so we've got some information. This thing is going to hit, the driver's going to hit the gas, and this thing is going to tear off, and it is going to go, let's see, our initial velocity is 0 meters per second. Our final velocity at the end of that period is 26.6 meters per second. And they tell us that that happens in a time period of 0.65 seconds. They want us to find the average acceleration of the dragster during this time interval. Now, they actually are doing a better job of it by calling it the average acceleration. We're going to do this exactly the same way that we've done in class before. In fact, this was one of the very first calculations that we did with actual physics stuff, because this is effectively our 0 to 60 information. We're going to see what the actual acceleration comes up to in just a moment. I will say this, in real life, cars don't maintain a constant acceleration. A lot of times as they shift from one gear to another, they'll actually change acceleration slightly. Everything that we've been doing up to this point, including this problem, kind of assumes that it's going at one average acceleration the entire time. The equations we would need to solve the exact real-life stuff is going to be a bit trickier, but this is pretty good and a pretty accurate representation of real life. All right, so now that we've got this information, let's go through and solve for this. We are looking for the acceleration. So if I were to, this is basically a kinematics equation, delta x, v final, v initial, acceleration, and time. Time is 0.65 seconds. My acceleration is what I am looking for. Initial velocity is at rest, and final velocity is 26.6 meters per second. Very close to 60 miles per hour. In fact, that's probably a close approximation that this problem is making. All right, we've done this one before. The thing that we do not have and do not want is our displacement, and so our equation will actually be, if I recall correctly, the first one from the kinematics equation sheet, and we find that the final velocity equals our initial velocity plus the acceleration times time. Final velocity is 26.6 meters per second equals 0 meters per second plus a times 0.65 seconds. This guy's 0, so he just kind of disappears, and then we divide both sides by 0.65, and we end up with the following. My acceleration is equal to 26.6, technically minus 0, but that's fine, divided by 0.65 equals a whopping 40.9 meters per second squared. Now, we haven't talked about this directly in class yet, but we will talk about it at least in passing. This comes up to 4.2 Gs. That's quite a bit. This is a very high acceleration. But here we go. There's our answer. The answer that it has listed for me is 40.92 meters per second squared. So this is all we're looking for in part one. It's actually just a kinematics problem, one that we have seen a number of times. Here's where it starts to expand on that. What is the size of the average force on the dragster during this time interval? Now, they're using the word average because, like I said, when the car shifts gears or does other things, the force will actually change slightly. We're imagining that we're just kind of taking the average value and treating it as though it's doing that the entire time. Since we now have the average acceleration, we can actually use that to find our average force. If I were looking at the car, I would have force of gravity downward, a normal force upward because it's not falling through the ground, and we would have some force propelling it forward. Strangely enough, that's actually the force of friction between the tires and the ground, but we'll just call that Fa. this is actually the average force that we're looking for. It's pushing the car forward and getting it to speed up. When I do my sum of forces in the x direction, I end up with, well, Fa. We're ignoring air resistance, and we're not hitting the brakes or skidding out, so we don't have any kinetic friction that we need to worry about. This is the only force acting on it, and so this will be equal to my mass times my acceleration in the x. Well, we just found that, well, we were given that the mass is 884.1 kilograms, and we just found that it had an acceleration of a whopping 40.9 meters per second squared. We found the force. 40.9 times 884.1. We end up with a very large 36,159, so we could call that, I'm going to go ahead and call it 160 newtons. To three significant figures, I'd round that to 36,200 newtons. It should probably accept both of them. Yeah, the actual online value that they have is 36,180, so it should actually accept any of those answers. Three significant figures, this would be 36,200. All right, now, we can find this because it's the only force acting in the x direction, so we're finding basically the net force. All right, the last part. Assume the driver has a mass of 70.3 kilograms. What horizontal force does the seat exert on the driver? Here's where we're paying close attention to the details, the inside stuff. Now, this would require us to make the dragster a system of several objects, the car and the driver and the seat for that matter, depending on how closely you want to look at it. But in this case, since we're asking about the force that is being applied onto the driver, well, this is a lot like the train car problems that we dealt with. We're basically looking at Cleophas. We can look for the simplest one. Well, the person has a free body diagram that looks like this. We have the force of gravity on that person. We have a normal force from the seat holding them up. And let's see, what horizontal force? This is where it becomes important. They ask the horizontal force, not the vertical. Now, we have a normal force of the seat holding the person up, but we also have the seat back pushing on the person's back to actually make them accelerate forward. We could call that force of seat back. Again, we just need a name for it. We could call it FA, like we did the other, force applied. Although since this is still part of one problem, I prefer giving new names to new forces so I can keep track of them. You can call it whatever you'd like. And then what we're going to do is, well, apply Newton's second law on this. Sum of forces in the x on the driver, because we're looking at the horizontal, is the force of the seat back. That's the only one, so it's going to be equal to the mass of the driver times the acceleration of the driver. Well, the driver is in the dragster, so, as we saw with the train car problem, they must actually have the same acceleration. Otherwise, the driver is either flying through the windshield or somehow falling backwards through the seat. Neither of those things are happening, so the force of the seat back is going to be equal to the mass of the driver, which is 70.3 kilograms, times the acceleration of the driver, which is the same as the vehicle, so that's 40.9 meters per second squared. Multiply those out, and we end up with the following. 70.3 times 40.9. 2,880 newtons. The correct answer that they have listed is 2,876. So 2,880 is perfectly fine. This is the force from the chair being applied onto the driver.